In this chapter, we're going to look at alpha substitution reactions. So if we have a carbonyl carbon, like so, and it's bonded to a C, which is bonded to something, including an H, like this is the alpha carbon. So it's one away from the carbonyl carbon. So this alpha carbon can undergo substitution reactions. Specifically, if we add an electrophile, all right, something with possibly a positive charge, but an electrophile, what we can end up with is getting C, double bond O, bond C, still bonded to two things, and now bonded to our electrophile. So the question we want to answer at the beginning of this chapter is, why is an electrophile interested in this carbon? Okay, so there's two ways that this can essentially be thought of. If we have this same exact setup that we had before, like this, we could add a base. Okay, and the base could potentially go after this proton. If the base is strong enough and it goes after this proton, this shifts here and this shifts up here. And what we end up with is something that looks like, if I could draw it properly, C bond O with a minus charge. This shifts here, this shifts up here. Double bonded to C, now bonded to two things. And if we were to draw a resonance form of this, what you would see is this can shift down and this can shift over. Remember that the minus charge has three lone pairs. And what we end up with is C double bond O, bond C with a minus charge, bonded to two things. This is now susceptible, the alpha carbon, to attacking the electrophile. And what we ultimately end up with is C double bond O, bonded to something, bonded to C, bonded to the electrophile, and bonded to two things. So by adding a strong base and removing this proton, we can get this. It turns out that there's another way to get this, and this is reversible. These are all reversible, and I'm not showing it very well, okay? But these are reversible reactions. We can also have something called the tautomer. And this is called a Keto Enol tautomer. All right. And Keto Enol tautomer is exactly what you'd think it is. This is a ketone group, right? Assuming that this is an H, assuming this is another carbon, this is a ketone. Enol is exactly what it sounds like. It has a double bond, and then it has a OH. So we have a C, alcohol, double bond C, bonded to two things, like this. So, like other tautomers we've seen, the H goes over here, and the double bond comes over here. So it's different functional groups, but the same atoms. Said another way, it's a constitutional isomer, but the functional groups have changed. And we'll talk in a minute about how this tautomer occurs. Well, we have these lone pairs on oxygen. If this comes down here and this kicks out and you have an E+, this could attack the E+. And what we end up with is a similar situation where we get C double bond O, bond C, now bonded to E, and two other things. So we can add the electrophile even without a strong base. Now, sometimes we do use a strong base and it's case dependent, but this is basically how this chemistry is going. What do you need to know? What we need to know is the alpha carbon is electron rich and can attack the electrophile. And I'll show you through resonance with this one, because we could do the same thing and draw a resonance form with a minus on this one in a minute, how you can get a similar type of resonance that you get here. But before we do that, I want to talk about a couple other things, including the mechanisms of how we can do this tautomerization. So let's just take one example. if we have cyclohexanone, all right, this molecule right here, it can tautomerize with its enol form. So the double bond moves here, and the H moves over there. So this is the keto, and this is the enol. Keto, because it's a ketone. Enol, because it's an alkene and an alcohol. Enol. So this is basically what we have. Now, if we were to look in reality, and there are ways to measure this, such as in an NMR, this is 99.9999% abundant, and this is only 0.0001% abundant. So the keto form is by far the more stable or the favored form, and the equilibrium definitely favors the keto. Let's look at the mechanism to convert from one of these things to the other. So there's two mechanisms. There's the acid catalyzed mechanism and the base catalyzed, but there's not supposed to be an R. All right, so it's the acid catalyzed mechanism and the base catalyzed mechanism. So let's start with the acid catalyzed. So we have R bond C, double bond O, bond C attached to an H and two other things. All right, and just for clarity, I'm not going to put a bunch of R's. So this is basically what we have. Now we add H3O plus. What's the H3O plus going to do? Well, we've seen this before. We have lone pairs on this oxygen, and these go here. And what we end up with is R bond C double bond O, bond H with a plus charge, bonded to C, bonded to two things, and an H, like so. This can resonate. So what's the resonance form of this? Well, we can have this come up like that. And now we have R bond C, bond OH. The plus charge is now on carbon, bonded to C, bonded to two other things, and an H. Now we can have some base, like, for example, water. And water can grab this proton, and that can shift over there. And at the end of the day, what we get is R bond C, bond OH, double bond C, bonded to two other things. Specifically, we get the enol. So an acid can help catalyze the conversion between the keto and the enol form. Note that the catalyst doesn't make this more stable, it just makes the rate of forming this faster. So let's look at the base catalyzed mechanism. We can also do this with a base, and as you could imagine, it works differently. So here we have R bond C, double bond O, bond C, bonded to two things, and an H. Exactly the same as what we had before, the keto form. And this time, we don't add H3O plus, we add OH minus. Well, in this case, what happens is this molecule grabs this. And what we get is R bond C, double bond O, bond C, bonded to two things. Now it has this lone pair and the minus charge. And this can resonate. This jumps here and that jumps up there. And we get a resonance form, so it's resonance stabilized if you will. R bond C, bond O, now with a minus charge. Double bond C, bonded to two things. Okay, now this is obviously going to be better to have the minus charge on the O than the C, so this resonance form is going to be more predominant. But in any case, this is a relatively strong base, so if we have some kind of H2O in solution, all right, we grab that, and what we end up with is R bond C, bond OH, double bond C, bonded to two other things. So we again, get the enol form of the molecule. So we can use acids or bases to catalyze the keto to enol conversion. So this is called a tautomerization. And again, it can be done with both an acid or a base. Now, as promised, what I want to show you is that we can look at this enol form and draw the resonance form of it. I didn't do it before because I knew I was going to do it here. So here we have an OH double bonded to a C, bonded to two things, like this. This can resonate. And how does it resonate? It resonates by this has two lone pairs. This drops in, this drops over. And we get R bond C, double bond OH with a plus charge, bond C, now with a lone pair and two other things, and a minus charge. Said another way, this carbon is E minus rich. Said an additional way, this electron-rich carbon could interact with electrophiles. And you'll notice that this electron-rich carbon is exactly one carbon away from our original ketone. All right, because remember, this is just the tautomer of the ketone as we talked about before. So this molecule is electron-rich at the alpha position. This is the alpha carbon. And we can then undergo these electrophilic reactions by having some electrophile, E plus, attach at the alpha carbon. These are called alpha substitution reactions because essentially the electrophile substitutes the hydrogen that was originally on this carbon. So what I'd like to do is look at one example here of an alpha substitution reaction that is catalyzed by an acid. So when it's acid catalyzed, we don't initially get the proton being removed and the minus charge on the alpha carbon. We get a C bonded to two things and an H like so. All right. And we're going to add to this an E plus in the presence of H3O plus. So the first thing we're going to do is we're going to get the tautomer. And the tautomer is R bond C bond OH double bond C bond H. Now if you want, you could write the resonance form of the tautomer. But what's typically done is this oxygen has two lone pairs. So if we want to show the mechanism of E plus adding to it, this drops in and this goes after your E plus. Okay, sorry, this H should not be here. This H is now here instead of here. Okay, so this drops in and this goes after E plus. And what we end up with when we do that is R bond C bond, double bond, OH, because we drop this in to make the double bond. Bond C bonded to two other things and bonded to the electrophile. This has a positive charge. So we're close to adding the electrophile at the alpha position and getting back the original ketone, right? This was our original ketone that we started with. But we have this H on here that we don't want. So some base, okay, it could be water, comes in, grabs that off, and what we end up with is R bond C double bond O, bond C bonded to two things and bonded to our electrophile. So at the end of the day, what we have done is we've added the electrophile to the alpha carbon. This is an alpha substitution reaction. We got rid of hydrogen, we added electrophile. We started with a ketone with an H here, we ended up with a ketone with an E here. And this could be a very useful reaction. So throughout the rest of this chapter, we're going to look at some reactions where essentially this is what we're doing.